looks like it started recording already. Okay, awesome. So we'll start now. So welcome everybody to the first week of the Transformers reading group. And I'll go to the next slide. This is our first week, and I didn't ask any of you to prepare anything, so it's fine. And this is also for my target audience is kind of for people who have, I don't know, you have trained a model in a hackathon before, but if you also want to learn more about other models used in text or just transformers in general, you don't really need any coding skills to attend this workshop. There will be no hands-on section in this workshop. So just sit back and chill. And since this is also the first workshop, I guess I'll be collecting feedback after this workshop to see what all of your skill levels are, to see if I need to simplify things more or just dive into more difficult papers that we can read for the weeks forward. And I am just another Waterloo student here. I'm just an exec, and I'm honestly not a professional in, I don't know everything about transformers. I don't know everything about machine learning. So if you feel like something that I'm talking about is wrong, feel free to correct me. This is a very, very open space. So just let me know, text in the chat, and I'll respond. And the goals of all 2, 3, 4 weeks of this reading group is to learn about the classical models used for text. So this week we'll be covering Seq2Seq, LSTMs, RNNs kind of. We'll also talk about the different parts of the transformer. This is mainly for this week. Almost half of this week's material will be based on just learning about the parts of a transformer and why they work the way they work, and also learn about the applications of the transformers. And this point, we'll be talking more for the few weeks forward. This week, if we have time, we will be covering BERT, and if not, applications of transformers would be for later weeks. Okay, awesome. And honestly, I covered this part already. This is today's outline. I'll be covering some really, really basic text models first, so LSTMs, and then Seq2Seq, and then I'll move on to transformers, and then BERT if we have time. Right, let's go into it. So let's first talk about why people use LSTMs for text usually, and why they don't use just simple ANNs. And when I say ANN here, I do mean artificial neural networks. Some people prefer to use DNN, deep neural networks, but we're referring to the same thing. So in TensorFlow, you'll be talking about dense layers, and in PyTorch, you'll be talking about linear layers. So it's just stacked neural networks. And they don't work because they don't store sequential data. So if you can absolutely do text classification using ANNs, it would just be very, very similar to using a bag of words. You're throwing some words in there and seeing some results. It will work, but you would not have the contextual information on sequential data. And that is somewhat fixed in RNNs. And when I say RNNs here, I mean current neural networks. They this type of neural networks, and they are better than RNNs at looking at sequential data, because when you look at ANNs, they usually just go from this red circle into this blue circles, which is, I guess, the cell or / the model, and then there will be an output. But for RNNs, they do something. They use a hidden state to feed back into the model that they can use to predict something further down the time point. And when you roll out AR and it'll kind of look like the image over here. So let's look at this one. So we put the first input. It can be anything from the first word in a sentence to, I don't know, first note in a music sheet, kind of, maybe. You put in your first word, and then you put it into an RNN. You would generate an output, but you also generate a hidden state here. Actually, can you guys see the red dot? Or,
yeah, we can.
Okay, awesome. That's cool. So you would generate hidden state that you would use in the second cell. So when you feed in the second word in the sentence, you use the hidden state from the first cell, and you output the second output, and so on. And this helps it basically use information from previous time points and use it for classification or whatever you use machine learning models for. And this also somewhat work, but when you look at longer sentences, then the problem starts to occur. And it is when you reach towards the end of the sentence, you start to forget about the first hidden state because the hidden state has been changed so many times, you just kind of don't know what it is anymore. And usually people call this phenomenon exploding and vanishing gradients. It not only happens in LSTMs and RNNs, they happen when a gradient is too big or too small. And that's when the models won't train well and they won't really learn anything. And the mathematical intuition behind this is, let's say you want to, for vanishing gradients, if you say multiply 0.9 over and over again, then you eventually get a really, really small number. And that's what vanishing gradients basically are. And exploding gradients are when you multiply some number bigger than 1 a lot of times, then it just gets really, really big. So as we all know, gradient is computed by looking at the gradient before it. So when we back propagate through time in RNNs, the gradient just, if there's a small gradient in the future time point, then the previous time point would start learning less and less. So essentially the first few cells in an RNN model would basically learn nothing. Oh, and by the way, I usually put links a lot in this PowerPoint. I would post the PowerPoint after this presentation, and you can click on the links. They are very, very helpful resources in learning just what these models are. Okay, next slide. And then we move on to LSTMs. And believe it or not, the first paper on LSTMs is actually all the way from 1997. It's the second link here. And I guess they didn't really catch on when they were first published because it does take a lot of computational resources. And some of you may know what AI winter is. It's when it's in the early 2000s when you have a lot of models. You have models like LSTMs, but then you don't really have the computational resources to actually use it and learn and apply it. So people were not that interested in LSTMs, but then the gamers came. People realized they can use GPUs for parallel computation, and then that's when machine learning models start catching on, and LSTMs were rediscovered and used. This first link is a very, very useful resource in learning what an LSTM cell is. So if today I did not explain very well, you can feel free to go into that link, and it's very there's a lot of pictures in that link. And you will learn better from pictures. Okay, so let's start this. Before we dive into the LSTM cell, let's look at some vocabulary that is used in LSTM. So when you look at the cell, you notice across means product, if you didn't know that already. And in machine learning, or really math, when you multiply one factor with another, it means how much you want to keep that information. So for example, in ABC times 101, you might know that it's returns something like A0Z. That just means the model is ignoring B and keeping A and C, if that makes sense. Another symbol that I would be talking about is the sigmoid symbol. It occurs a few times in the LSTM cell. Basically, what this is an activation function, and it returns output from 0 to 1. So I think it's this graph. This is the sigmoid graph, and it goes hand in hand with the product intuition I just explained. So whenever model outputs something that's closer to 0, then the more it wants to get rid of that particular input. And the closer it is to 1, the more you want to keep something. Tangent, hyperbolic tangent is kind of the same thing, except it goes from 1 to -1. And I'm pretty sure this first order derivative of tanh goes further before we use 0. And it's used twice in an LSTM cell. If you look at the top bar of an LSTM cell, you would see CT-1 and CT. Those are the cell states in a LSTM cell. And if you look at the bottom here, you would see HT-1 and HT. Those are the hidden states of an LSTM cell. And the difference between cell state and hidden state is usually you think of cell state as a long-term memory. So I'll get into this later, but essentially this is basically the input unmodified. So think of a conveyor belt that runs from the beginning to an end. You keep the same kind of similar information from the beginning to end, so you don't lose as much information as you would in an RNN, where information is kind of rewritten over and over again. And hidden state is basically carries the information that you need almost immediately. So think of it as a short-term memory. So LSTM, long short-term memory, means this is the long-term memory and this is the short-term memory. Cool. And W means weights. Usually when we have weights, that means we're training something and it learns. Cool.
Just one question.
Yes.
Why in the previous slide, why was there like 2 outputs for the hidden state, right? Shouldn't it just go to the next cell? Like, you know how there's one in the top right and also one in the bottom right?
Oh yeah, I think it's just like they use this as an output and then they feed this into the next cell.
Oh
yeah, I think it's
just. I guess that's the output too. I guess. Oh, okay.
Yeah, like they're the same thing, but yeah, like you can use this and then this feeds into the next cell. Yeah, I guess it's just how they draw this picture. Oh, and in this one, I guess they have it too. Okay, let's start looking at this LSTM cell. One thing that the LSTM cell does way better than RNN is the long-term memory. And as I mentioned, it has to do with this line, which is the cell state. And if you look at what happens along the way, you only see a multiplier, and then you have information added to the conveyor belt. And then this one kind of goes the other way, so it doesn't really matter. So the information is kind of goes a long way without a lot of modification. So that's why they are better at looking at long-term information. I will talk about what these means later. We'll first look at this gate. This one, we call this the forget gate. And it's literally what it is. So you have inputs here. If it, okay, I'll go through it basically first. A forget gate forgets the information that you need. An input gate gives, I guess, selects what inputs to be used, and the output gate selects what outputs to be used. And if we dive into the math for forget gate, we would see an input xt, so that would be your word, each word, ht minus 1, which is the previous hidden state. We feed that in. We go through a sigmoid layer that we train weights. And if we recall, sigmoid layer returns something from 0 to 1. And when you multiply something from 0 to 1 with something, it selects something. And in this case, it would select something to forget. Because if you think about it, if you output more zeros, then it'll forget more stuff. And if you output more ones, then it'll remember more stuff. And that's the forget gate. The equation used is the first one here. So the weight multiplied by the inputs, and BF is just a bias. So think of it as y equals mx plus b. B is just bias. It's also a part of the weights sometimes. It's also learned. And then you put a sigmoid function over it to generate something from 0 to 1. Okay, let's go into the input gate. This is slightly more complicated, but it's also not that complicated. You also have your xt and your hidden state from previous cell. You go into here, you go into this sigmoid cell, goes it outputs something from 0 to 1. You go into this tanh, you have something from -1 to 1. And then you multiply them together and then add it to the cell state. So essentially what it does is selects information from the hidden state and decides whether something is important to add into the cell state. Yeah, and the output gate basically works the other way. It uses the cell state as input. It goes through the tanh layer and also the sigmoid layer, and they multiply them together and selects what would be used in a short-term memory, and they have it as the hidden state. For the input gate, the equations are here. So I stands for input. And then it's also just weight times input plus bias. For output, it would be here. Yep. And yep, that's all for this slide. Next slide. So some limitations of LSTMs. The problem with LSTMs is that they still cannot process like very, very long sentences. I think what we mean by long is usually somewhere between 200 and 300 words. And I think researchers have found that experimentally, if you train something longer than, I think 300, don't quote me on that, but it's around like 300 words. If you go longer than that, then it's kind of just doesn't work as well. Like it also forgets stuff. And there's a model called bidirectional LSTM, and it actually kind of helps because what a bidirectional LSTM is, it basically goes through this process. This process, except it also goes through this process backwards, and they concatenate the outputs together. So there's a forward pass, there's a backward pass. You add them together, and they just remember stuff better. There's also an attention mechanism that helps in an LSTM. We will talk about this later after Seq2Seq. Also, if you have trained, say, some CNS before, you know that sometimes you can take, I don't know, a mobile net, train it on dogs and cats, and then you can use the same inputs and fine tune it for cancer detection, for example. But for LSTMs, we don't usually do transfer learning, and that kind of sucks because for every topic we want to train, you have to train it all over again. I'm not saying it absolutely needs to, absolutely does not transfer learn. I'm just saying it just doesn't work very well. It also takes very, very long to train LSTMs because you have to train it word by word. Like you feed in the first word and you wait for this first hidden state and the first context, cell state, and then you feed in the second word, and then you wait for its cell state and hidden state, and so on. And that kind of, it just takes a long time to train, and it's not very, very efficient. With that said, they are actually better than deep neural networks and our recurrent neural networks. Next slide. Encoder-decoder structure. When we talked about LSTMs, usually what people use stacked LSTM for is for classifying sentiment analysis, like classification models. But for encoder-decoder structure, we look at multiple, like a sequential input and then a sequential output. And examples of this would be machine translation. You feed in English words, it outputs French words, or speech generation where you just feed in English words and it outputs a sequence of noise or sound. And that's what encoder-decoder structures do. There are two papers that kind of talked about encoder and decoder structure / Seq2Seq. Basically what it does is the encoder part is your standard LSTM. You feed in the first word, get hidden states and cell state. Feed into second word, you get cell state and hidden state. Third word, cell state and hidden state. And once you reach the middle, we call this thing context vector. And basically what it does is just it remembers the information from all the inputs that you have input before, and then it starts generating the output. So for outputs, you would feed in, you won't feed in anything. You feed in the end of sentence tag plus the previous context vector. You get the first word of the output. You use the first word of the output. You feed it in. You get the context vector from before, and then you get the second output. There are two ways that, or I guess there are more than two ways that can be trained, but there are two methods that people use to train encoder-decoder structures. Some people, they don't care about what the outputs could be during training. So the first output could be nonsensical, sensible. You feed in the nonsensical output and you hope it generates something better. And the second way of training it is whatever you output for the first one, you feed in the right answer to get the second output. And this is called teacher forcing. It's kind of effective. It's kind of nice. And something that I found really fun when reading the papers on sequence LSTM models is that they actually reverse the order of words when they feed in the input, and it actually works better. And they said this is because when you feed in words in reverse, the first word would be closer to the first output, which is supposed to be kind of linked, or like when you try and translate something, usually the first word would correspond to the first output. So the closer they are in the sequence, then the better they are at generating the output. About this paper. And then we will move on to attention in encoder-decoder networks. Attention is very important when talking about transformers, because the paper is literally called "Attention is all you need." But this is not exactly the attention that we will be talking about in transformers. In transformers, we use something called self-attention. But for this attention, we mostly use it for the encoder-decoder Seq2Seq LSTM model. You might have noticed that I'm avoiding this word because I do not know how to pronounce it. So what this attention does is basically it links the input and output in a way that makes the model more focused on like each input output. So if you look at this image over here on the right, you can see the attention mechanism at work. So I think the task is translating either from French to English. This is the French sentence, this is the English sentence, and you can see, okay, I just got a notification that the meeting would end in 10 minutes. If it ends, just join with the same link. You would see that the words that are related would have a higher attention that is indicated by a brighter block. So LE is the accord is agreement, and you can see it's basically a diagonal line of blocks, except these three, which are kind of reversed in French, but they are in order in English or the other way. So zone would correspond to area, and this is the block that has attention in it. Economic, and the European corresponds to this one. And the mechanism is actually kind of simple. So it's just basically this equation. S is the decoder hidden state, H is the encoder hidden state, and alpha is kind of the attention scoring function. So when you look at the previous slide, actually, it's better not look at. Is it? Okay. So in here, we would get a decoder hidden state, I guess, in each of these arrows, and we call them S. Each of these arrows is H, which, sorry, the other way. These are the decoder hidden states, because this is when they start to decode the context vector. So decoder hidden state, they are S's, and these are the encoder hidden states, so they are the H's. In this function, they basically multiply them together and then use an attention scoring function. It's, I think, a softmax function that can be trained to generate a context. Okay, to generate a context vector that will be used in the second input of the decoder network, if that makes sense. So instead of the context vector feeding into this block directly, they would have arrows going from here to here, and they would have attention mechanism here, and before they feed it into the decoder block. And that helps with identifying which words in the sentence are important when you're at a certain output state. Okay, now transformers. Like I said, this is the paper. The title is called "Attention is all you need." by Google, and there's a U of T Chi here. Let's dive into it. This is the transformers model, the one on the right. And it might look very, very complicated, but it's not really. When you look at transformers model, you can split it right down the middle. This side is the encoder side. So think Seq2Seq, Encoder-Decoder. This is the encoder side. This is the decoder side. And another thing that you can notice very quickly in a transformers model is that there's these residual connections, and they're kind of like the cell state in an LSTM, except they are unmodified. You just feed them from input to output just to keep your connections. And you might have seen that in a ResNet. This is a ResNet block. ResNets are used for image classification tasks, and they feed the input right back towards the output just to keep that information and not lose it. In this picture, you might have also noticed attention, multi-head attention, and also masked multi-head attention, and also positional encoding. And we will be decoding those words in a minute. And I think the easiest word to decode is masked attention. Basically, you would see that it's only happened on this side in the first one. And basically what it does is it hides the information that you will not need yet. So for example, when you're training a model, English to French, you would not feed all the French words into the output because you don't know those yet. You would only feed the words that were already classified back into the model, or it will be cheating. Yeah, that's what mass attention is. It just masks out the words that you would not have in the model yet. Self-attention. This is slightly complicated. So if you don't understand, just let me know. Attention mechanism kind of works the same way on a higher level. You're linking the input words to each other just so you can understand the context of each word in a sentence. So for example, if we're talking about a bank, if you don't understand the other words in same sentence, you don't know if I'm referring to the institution that helps you store money, or is it the kind of geographical feature close to an ocean. So if you have, say, money in the same sentence as bank, then you probably would think that the bank would be referring to banks. And that's what self-attention helps in the model. And hello, people. Welcome back to this reading. I will recap this attention because I feel like I did not explain that well. So each word in a sentence would be multiplied by each word in the sentence as a key. So each word would have a query. Each word in a sentence would have a key. You multiply them together. It'll be a matrix of a lot of different values. If you expect those two words to be related to each other, to be kind of useful in classification or later on in the model, the attention mechanism would be brighter, it will be a higher value. And if they're not that related to each other, then there'll be a smaller value. And I think I said we ignored the decay term in the last meeting. That is just for, I guess, normalizing this multiplication. And normalization is something that people usually do in machine learning because when you have inputs that are within a certain ranges. It's easier to train in the model. And what multi-headed attention is just a lot of different attention. So in the paper, we actually have 8 of these heads. You have 8 of these attentions. You concatenate together, and then you use it in the model. And it actually works pretty well because each head would be looking at different kinds of information. So for example, maybe the first attention head would be looking at grammar, and the second would be looking at vocabulary or stuff like that. And yeah, basically you're getting a different attention in different contexts, and that helps with text, learning about text. It's good to mention that attention is used in the encoder. So between each input word, there would be attention. Between each decoder word, there will also be attention. And there's also attention between the input words and the output words. And we call that one cross attention, actually. But if it's within the input words or within the output words, then we call that self-attention.
And then where is this attention like used?
Oh, it's here. So I guess at the very beginning, you just feed those input in. You determine whether these words are related to each other, and then you move on forward with these feed or forward layers, which are just your basic dense layers. And
I see.
Yeah. And this kind of never mind. Okay, let's move on. Positional encoding. I think I wasn't very clear. I guess I didn't mention it in the beginning, but in transformers models, you actually put all the input words in at the same time. So you might know that in LSTMs, you feed in the first word, you get the second first output, you feed in the second word. But in transformers, all the words are feed in at the same time, and in that sense, you actually don't know the relative position of each word to each other. So kind of the same problem that deep neural network would have. And they mitigate this problem by having positional encoding. This might also be a difficult concept, so just bear with me. My first explanation might not be good. They decided to use sine cosine to represent the position of the word in the form of a vector. So it's kind of like attaching the number 1 to the first word, or attaching the number 2 to the second word. But that doesn't work because 1, 2, 3, 4. If the number of words in a sentence gets bigger, then it's kind of hard to put that in the model. And they decided to use sine cosine because it is inspired by the Fourier series. I would not be explaining Fourier series, and I might not be understand Fourier series, but it is inspired by the Fourier series. And basically, what it does is, so for each position, you would feed in pulse, and then for I is just the dimension of the input. So what's a good way of explaining it? Actually, just look at this graph. So this graph is just these two equations, but graphed out. So i's would be along this dimension, and the position would be along this dimension. So let's say you're looking at the first position, you would glance across this line and use that and you add it to your input to represent that this is the first position. And then you might notice that each position is kind of different across these dimensions. And if you look at, say, the 10th position versus the 11th position, you would be able to determine that they are kind of next to each other because of how the way these sine and cosines work, because they're continuous, right? So you can just compare between two positions and know which one is before each other, whether they're close, whether they're far. And this provides context to the model when training. Blah, blah, blah. Okay, I covered those. Cool. Next slide. And so why do people like transformers better than LSTMs? Well, first of all, it's cooler. They just sound cool. They sound like robots. LSTMs sound like a short form of a very long word. That's not very cool. And as I mentioned before, transformers feed in all the text in a sentence at the same time. So that provides a lot of opportunities for parallelization. And as I've mentioned before, GPUs are really good at parallel operations. So when your model can process stuff parallelly, it trains faster. It's just better. And in the attention mechanism, unlike LSTMs, where you pass the hidden state from the beginning to the end, and you start to lose information when the words are far. In self-attention, the position of the word in a sentence doesn't matter because they're just computed the same way in a matrix. So even though if the words are far, you can still derive like a relationship between them. And that's why people use transformers. And we can look at some results that the transformers have in the paper. In the paper, they use transformers to translate English to German and English to French. And I think it performs really well. Yep, the BLEU score is basically, think of it as accuracy, how accurate it is at translating English to German. So it is the higher, the better. So you can see it's better at developing these models that are considered state of the art at that time. This model, Deep ATT, uses bidirectional LSTMs. GNMT also uses LSTMs with attention. This conf S2S is actually kind of interesting. They use CNNs to translate from English to German. And yeah, I always find it very, very cool when you use some models that's usually for other purposes and use it for another purpose. We can also look at the flops. So flops is just how much it costs to train, how much work it does, how much effort it takes to train. So the lower it is, the better. And we can see that transformers actually use a lot less operations than other models would take to train. And that's actually very good news because you're using less resources to produce a better result, basically. I guess I'll add a commentary on BLEU score. BLEU scores are not necessarily the best way of determining accuracy, and you might not see BLEU score being used in other papers that will be discussing this term, because they just look at words but not look at the meaning, if that makes sense. So you can translate the sentence perfectly, but if you're using other words, then the BLEU score would be pretty low. But I guess this paper is not use BLEU score, so it's fine. 454. Okay, let's just end the meeting here then. We'll talk about BERT next time. It's pretty similar to transformers, but they're just using a different way to train it, so it learns more stuff from the senses. We'll also be discussing other papers next meeting. I haven't selected them yet, so I'll be selecting them over next week, and we'll talk about them later then. Cool. Does anyone have any questions?
So is BERT just not like a specific type of transformer, or is it something more?
BERT, I guess we can move forward. BERT doesn't really add a lot to the transformers model. It's basically just the encoder part of the transformers. It's just the way that they train it that's different from how you would train a transformer. And I guess the inputs and outputs are kind of different. They also don't use the same positional encoding as transformers. They're using, they're just using different encodings than transformers.
I see.
Yeah. And if you know, GPT has been making news in the text processing community because it's just really cool. GPT uses just the decoder part of transformers. And yeah, BERT uses encoder, GPT uses decoder.
Well, I have the GPT-3 beta, and it's really cool.
Yeah, it is. Okay. Suggested papers. Oh, I'll be posting this PowerPoint in the somewhere. I guess it will be on Data Science Discord, and this video would also be uploaded to YouTube. And in the links across the slides, they're all like very useful resources in understanding how transformers work. So D2L is always a pretty good resource in learning machine learning models. The RSIF links are just the original papers. When we talk about transformers, there's always one link that people usually refer to. Let me see if I can find it. I'm pretty sure I included it somewhere. Oh, it's this one, illustrated transformer. It basically, it's also very graphical. There's a lot of pictures telling you how the matrix multiply to each other. And yeah, you learn really well with the illustrated transformer. There's also the, annotated transformer. That's very useful. It's by Harvard. It's basically like a Jupyter notebook. It goes through all the steps in PyTorch in a transformer. I'm pretty sure transformer has, am I still? Okay, wait, transformer, and then, yep, they have a pre-built module now, so you don't have to go through all these steps to use a transformer, but it's always good to look at how they implement these models. Yeah, so this is annotated transformer, and if you, yeah, recommendations for exercise to practice implementing the stuff hands-on, and they'll like, okay. I guess the best way to learn transformer is just or like learn any models in general. It's just going to Kaggle, find a data set, and then use transformers, if that makes sense. If you go to Kaggle and look at sample notebooks, there's always steps. Or You know what? If I'm since there's like two questions about using transformers, I might go through using it next week, but no promises just yet.
Yeah, I would be interested in something like that too.
Okay, cool. Then I might do it.